The drawing shows two perpendicular, long straight wires, both of which lie in the plane of the paper. The current in each of the wires is I equal to 5.6 ampere. Find the magnitudes of the net magnetic field at point A. This question is from the chapter Moving Charges and Magnetism. Okay. Now, here we will have to use the concept of Biot-Savart's law or the Biot-Savart law we have learned in the chapter. Seeing this figure, you may get a little bit confused. They're asking you to find out the magnetic field at the point A. So does this point B have any significance there? Absolutely not. No significance at all. Okay. Now, tell me how to solve this question. Okay. How to do it? Now here, in this question, it's very important that you read the question carefully. There's a small word hidden there, which will make the question very simple. And what is that? Can you tell me? In the question, in the first line, there was a term or a word like this. A long straight conductor. It is a long conductor. Whenever you hear the term long conductor in a question, understand that they are actually referring to an infinitely long straight current carrying conductor. And tell me, what is the equation? What is the condition for the magnetic field of an infinitely long straight current carrying conductor? That is mu 0 I by 2 pi r. Right? So by using this equation, for this and this, for both the conductors, we can actually find out the magnetic field at the point A. But one more thing that you have to take into account there is the direction. Now, to find the direction, we can make use of the right hand thumb rule. Okay, so if I keep my finger in the direction of the current, the direction in which I curl my fingers gives the direction of magnetic field, right? So for this conductor, I'm curling like this. So it will be into the plane at the point A. So I'm marking it with an into. And for this conductor, again using thumb rule, I'm curling like this, right? Keeping the thumb in the direction of the current. So I'll be getting over here, it will be out of the plane. And tell me, as you can see from this figure, which conductor is closer to A? Which conductor? This one, right? I can call it conductor 2. This is conductor 1. So conductor 2 is actually closer to the point A. If the conductor 2 is closer to the point A, from this equation, it's very clear that if R is less, closer means R will be less, then the corresponding magnetic field will be higher or greater, right? Therefore, we can write that the net magnetic field at the point A will be equal to B2 minus B1. It is B2 minus B1. And now substituting the values, we already know that the same current of 5.6 ampere is flowing through both the conductors, right? So I can be taken outside. So mu 0 into I by 2 pi R, right? So first one 1 by R2 minus 1 by R1. Now let's substitute the values here. This is equal to 4 pi into 10 raised to minus 7, the value for mu 0. I 5.6 divided by 2 pi. Fine. R2, what is the value of R2? It is 0.2, right? Now 0.2 can be written as 2 by 10. Fine. Or this is equal to 1 by 5. Right? We can substitute that here. So we'll be getting 5 here. 1 by R2 will be, R2 is 1 by 5. So 1 by R2 will be 5 minus. Similarly, R1, it's 0.4, right? So 0.4 can be written as 4 by 10, or this is equal to 2 by 5. Clear? Or 1 by R1 will be, this is actually R1. So 1 by R1 will be 5 by 2. Okay. Now simplify this. 2 pi and 2 pi goes. There is a 2 coming over here. 5 minus 5 by 2 is what? 5 minus 5 by 2 is 5 by 2 again. So upon simplification, you will be getting the answer as BA will be equal to 28 into 10 raised to minus 7 Tesla. So the magnetic field at the point A due to these two long current carrying conductors is equal to 28 into 10 raised to minus 7 Tesla. Okay, clear? So please do remember the corresponding equations for a semi-infinitely long conductor and for a long conductor. Okay, sometimes in the question it may be the perpendicular bisector that is asked. So remember the conditions for that also. Okay, so I hope it's clear. In case you have any doubts, do comment below. Okay, thank you.